Epifanio for his second talk.
Thank you very much, John. And the only reason why I'm here, just to give my second talk, is by way of a punishment. So I will not tell the reasons why I deserved this punishment, but why it is reciprocal in a way. So I mean, by the law of propagation and symmetry in punishment. Hiroshi and I couldn't compare notes last night for one good reason. And the reason is that both lectures were still evolving last night. So his lecture came to me as a surprise, and my lecture will come to him as a surprise as well. This might be a kind of red tape through this workshop, at least as far as I'm concerned. Essentially, I will pick up from Hiroshi's statements, and first of all, I think there are two important things to say. One is that K13 and the whole history and about it has to be intimately related to the ground state. I think that this is something that I learned from his paper, and I also think that this is a fundamental issue. And I'll try to elaborate on this idea, and toward the end of the talk, if time permits, this is my third item in the list. If time permits, I'll try and explain to what extent the suggestions that I got from this problem and will have taught me something in terms of building another more complicated model. So I think in this sense, I think that the infamous K13 case are still something to teach us. I agree perfectly with Hiroshi from different point of view that K13 must be set equal to 0, and I'll try to give some further reasons in favor of this. I'll make some quotations for. There's another reason that there are many reasons that distinguish me from Hiroshi. One of these is that I'm not at all politically inclined, so I can freely say whatever I think. Of course, I will repent and be punished as a consequence, but I can't stand doing this. All right. So how does it come? Well, just to link this second lecture of mine to my previous one, the idea is that in this context, we believe that Q is represented in this uniaxial fashion and is a nematic director, and it is inherited, so to say, from this quadrupolar tensorial description. And what we say, we simply say, right, we formally set S identically equal to 1, and in this way, we formally recover the usual expression that Chuck today has shown us in terms of the distortions induced by the director field. We derive them from a more general theory that would feature only the distortions in Q once Q has been given this form. Again, this formula, this Franck's elastic energy density, has been shown many times, and has appeared many times on the screen, so I will not comment further on it. But this is a K13 term, which is written in this direct vector notation. It is a divergence of the divergence of n multiplied by m. And of course, so we'll see in a moment what peculiarities this term has, which actually make it very different from the other K24 term. I mean, most of the time, this what I call the K24 has been named K4 by Chuck, who I think followed my book. So I changed my mind in the interlude. So I come back, I rewrite this term, and I wish to just to remind you what the meaning of these constants is, this K1 is a splay constant, K2 is a twist constant, K3 is a bend constant, K24 is a saddle splay constant, and this K13 is also called the splay bend constant in the literature. This is a one constant approximation. We have been already exposed to it. We need to take all three, K1, K2, and K3 equal to K, and K2, 4, and K13 equal to 0 in order to get this special expression for the elastic density energy, which is beloved by all people who have done harmonic maps in the past. So the free energy functional then takes this form. Again, B is the region in space, and B is the volume measure. And now we come to give these terms the proper name in the calculus of radiation. So this has already been shown. The trace of grad n squared minus the divergence of n squared can be written as a divergence, but it is a very special divergence. It is a divergence very different from the one we are going to which has already appeared for the K13 case. And the reason is the following, that once you perform the integral over the whole region B of this difference, eventually by using Gauss' theorem, you can write this as the flux of this vector through the boundary, and nu is the outward unit normal. But the point is, and this is not completely trivial, the point is that all these gradients that survive on the surface are only surface gradients. So they do not contain the normal component of the derivatives. So this means that once you know the field n, and if you know the field n on the boundary, then these gradients are completely frozen and they are completely known. So this means that for all intents and purposes, this is not just a surface term, such as the K13, but it is more than that. It is a surface term whose integral on the surface eventually depends only on the trace of the function on the surface. And this is an explicit, distinguished character of the K24 term, and this is the reason why the K24 term is perfectly acceptable from the point of view of the calculus of radiation. All right, what does happen when... Sure.
Go back.
Sure.
So there aren't enough indices in that expression.
No, there shouldn't be any.
Well, how does n impact?
There shouldn't be any.
Sure. Grad n times n.
Where?
That term.
Yeah?
No, on the right.
On the right, yeah?
No.
Up a line.
Up line.
Yeah?
One more over to the left. Left.
No.
No.
You're skipping it.
Grad n.
Right around it.
Divergence of
Grad
grad
n
n.
Grad n times n. What do you mean by that? You mean
The tensor.
You hear? The grad n is a tensor, isn't it? And so it operates linearly as any tensor should do on the tensor n, on the vector n. So it reduces the vector, and this is divergence computed over the whole thing.
And on the other side.
This is
Going to change the gradient and that right.
no, I didn't. This is a trace of grad. This is a trace of grad n squared. So it is a number, and so this is the square of the divergence of n, which is another number. And this is a divergence, which is a number.
And you write it with components, Epifanio?
Oh, come on. All right. Well, this is my punishment. You see? I never use components, and now I'm forced to. All right. I don't know whether I can do it. Sorry? All right. Surface gradient. So the surface gradient, is this what you mean, or even before that? The grad n correct? This is the vector, isn't it? This is the vector I call the I component of this. And the I component of this is ni, j, nj, saturated over j.
It's basically n dot grad operating on it.
Or n dot grad is...
If you turn it around,
It's the curvature of the integral curves of n, right?
If you wish.
The same as curl and cross.
If you wish. This is a geometric interpretation, but I mean, may I? I didn't think that this.
Carry on.
I didn't think that this would raise so much. Anyway, all right. So this is a number. This is a divergence, and the important point, which is not easy, and which is is easy, I think, was first remarked by Jerry Erickson, which is not trivial, is that this operator, actually, this differential operator on the surface contains only surface gradients, surface derivatives. And so this is the key. All right, if you do the same thing, now this is a divergence of n times n. So you take the divergence, this is a K13 term, to take the divergence of this vector, and of course you can integrate it over precisely by using Gauss' theorem, and you end up with this expression. Of course, the full divergence on the surface can be split into two terms. One is the divergence, the surface divergence, again the one that depends only on surface derivatives, and the other is a normal derivative, the normal divergence, which depends only on the normal derivative. Now, of course, as you see, there is one thing here, one little bit, which is which depends only on the trace of n on the surface, but this little bit doesn't. So it depends, its fields in a way, the behavior of the field are underneath the surface, to put it in physical terms. Sometimes, I mean, I've seen in the physics literature many times this behavior referred to as a subsurface distortion or the subsurface deformation of the vector field. It is just precisely mathematical term. It simply means that this surface integral depends on the normal derivative of the field. All right, this is precisely what I have already anticipated. In the presence of strong boundary conditions, when the field n is prescribed on the whole boundary, then these derivatives, these would be the tangential derivatives. If I take the surface gradient of n and I apply it to a unit vector in the plane, in the tangent plane, I obtain what is sometimes called the surface directional derivative of n. All these directional derivatives are prescribed because I know the field, the n field on the surface. And so this means that the normal, that these derivatives are prescribed. They are prescribed in terms of the field n, while the normal derivative, which would be this quantity here, this vectorial quantity here, is completely free. Of course, only one bit of this enters here, and it is a bit which is projected along the normal itself. All right, a bit of history. I will comment briefly on a few contributions to the case. I will not cover all contributions, and I'll simply concentrate on those contributions that in a way serve the purpose of making my point, which is what most historians do. Apart from our. All right. Or then first introduce. Sorry?
I didn't catch that.
Or then, well, I was asked to make it a little bit light because it is a long afternoon, so I tried to say more jokes than needed, maybe. So, or then in 1933 introduced this K13 on a purely phenomenological basis, and the argument was precisely the one that Hiroshi gave in his lecture. It had to be accounted for just because 1 over psi squared. It is a term which has the same sign, it's the same order as 1 over psi squared. So this is the idea. So a linear term in the second derivative should be accounted for on the same ground as the quadratic term in the first derivative. So this is the belief. Of course, it is not grounded. But anyway, this was the belief. And on the basis of this belief, Ozen introduced this K13 term. Frank I read his paper several times. He simply omitted it with no explanation whatsoever. And so it was completely removed with no explanation. The first reappearance, at least to my knowledge, was in 1971 in the Melvin-Zaupe paper, which was introduced on the basis of a molecular argument, which also implied this Cauchy type relationship between K24 and K1 and K2. And then there was the first emergence of what is at that time was called the Oldano-Barbero paradox, which was proposed in 1985. And they simply produced an example, which is, I think, the example that Hiroshi showed you at the beginning of his lecture. They showed by example that K13 makes the elastic energy functional unbounded from below. It was just a sequence of distortions that would, in the limit as one parameter tended to 0, would induce a divergence to minus infinity of the functional. This was the argument. All right, and then there were several attempts to remedy this, and of course one possible avenue was to add terms which were quadratic in the second gradient. So the idea was, all right, we have phenomenologically accounted for second gradients already in the linear form. Then in order to remedy this, we needed to go and employ terms which are quadratic already in the second derivative. Of course, the terms, I will not attempt to make a list of all admissible terms, admissible in terms of frame indifference and nematic asymmetry, because there are a lot. And this attempt was first made in these papers, as far as I am concerned. And but actually, they were a little bit well. They didn't quote this other paper by Brandon Plania, who came first, as always do. And because in a different context, actually, in symmetric theory, they had already introduced quadratic terms in the second gradient, and essentially these developments go along the same line. All right, this is my comment. Of course, there is one problem with this line of approach, which is again purely phenomenological, and the problem is that there are plenty of these terms, and so there's no reason why you should privilege one at the expenses of many others. But there is another problem, and if you look carefully, it is not enough to insert into the picture one of these extra terms. But you need to be sure that the phenomenological constants that they carry along into the picture are appropriately chosen, because otherwise you would not avoid the unboundedness from below. So in a way, you want to solve a problem, but you bring in plenty of admissible solutions, and each of them will bring another problem. So this doesn't seem to be the way to go, even on purely phenomenological grounds. Well, there is another approach. This was quite extravagant, I would say, but it was a nice paper which I enjoyed reading. Actually, Peter made me read lots of papers to prepare this lecture. And the idea was, all right, we have pinpointed the thing that goes wrong, which is a normal divergence of n, and why don't we simply throw it away? Again, it is based on a phenomenological argument, which is just convenience argument. And of course, this can be done, why not? But it is clearly an ad hoc solution. The idea was just to be more specific. The idea was just to come back to this explicit representation and throw this away. There's no justification whatsoever. Of course, all problems were solved, but the remedy was lacking any rationale in my view. All right, and then there was, I think that this was the first move towards realizing, actually towards proving that K13 is actually vanishing. And this has to be, has already been shown indirectly and more powerfully by Hiroshi in his lecture, but I think it was first realized a couple of years earlier. And sometimes people call this the Somoza-Tarazona paradox. It was a time of paradoxes. The Oldano-Barbero paradox produced another paradox, and this paradox was simply based on the fact that these people, for the first time, to my knowledge, realized that by performing a different change of variables in that integral, essentially by choosing a different value of gamma in Hiroshi's talk, they could make a K13 whatever they wanted, and so they said, all right, then the right choice is to set it equal to 0, because if it is not gauge invariant, this was their language, if it is not gauge invariant, then it makes no physical sense at the macroscopic phenomenological level, so we throw it away. All right, and then this interesting paper, which came out approximately at the same time as Hiroshi's, and they claim, Faeti and Faeti, I think it is the only paper Faeti wrote with his son. So this is the reason why it is a double Faeti paper. They argued that one possible explanation of the Somoza and Tarazona paradox would come from the fact that surface effects had not been taken properly into account, namely that in the language of Hiroshi, those integrals that Hiroshi computed toward the end of his lecture could not and should not have been computed up to infinity, but up to the boundary, to the surface. And this, of course, had an effect on the K13 term. But at the end of the day, there is a nice, very long discussion, and this is the reason why I'm quoting this paper, because I was intrigued by the long discussion that they made at the end of the paper, where they insisted in distinguishing between the molecular interaction energy from the phenomenological free energy. So in a way, they stayed at a distance. They said, whatever we have done here, whatever implementation of the K13 term we have done here is not, by all means, is not necessarily reflected into the free energy. And this, I'll come back to this point once more, and it was touched upon again by Hiroshi in his lecture, when he said, well, in order to compute in his approach, in his rigorous approach based on DFT, he said, well, look, in order to compute the free energy, you need to take the difference between these two omega, the omega functionals. And so it is not just the same thing as computing the average interaction energy. And this, I think, is another key point, which for people who do phenomenological theories and continuum theories, I think must be a kind of guideline. Because either you do things rigorously and properly on the microscopic level, as Hiroshi did, or you might use these microscopic arguments, this is my view, as inspiring arguments, but your inspiration should not be taken too seriously. And I'll try to make this point clearer in the rest of my lecture. And of course, everybody knows now at this stage what it was in Hiroshi's paper and the major conclusions that he drew. I was really very interested in reading this paper, because once again, it pinpointed this difference between computing the total interaction energy and computing, from a microscopic point of view, the free energy of the system. These two things are different, and they are too often confused. All right, but of course, K13 cyclically resurrects, and I'm quoting this paper actually there's a series of papers where, again, different approaches, microscopic approaches, have brought K13 into life again, though, I mean, by reading, again, carefully these papers, the authors are completely aware of the fact that the K13 behavior in their theory is completely different from the behavior of all other constants they have computed. So once again, I'm not able to explain in detail the differences between these papers and Hiroshi's paper, but certainly the authors themselves are aware that the K13 term as, or the derivation of the K13 term they've given is open, as I said, to suspicion. All right. This is, I don't think I need to go through this argument again, but this would be the link which has already been illuminated quite effectively by Hiroshi between the existence of a K13 term in a phenomenological theory and the undistorted state. So if we believe that the undistorted state is homogeneous, this is the argument that Hiroshi has given us already in his lecture, and simply shows that this linear bit, not the whole thing, because if you compute properly this quantity, you will see that it splits in one term which is similar to the term that come into the K24 term, and something which is different. So there is always a kind, even at the phenomenological level, there is always a link between the K13 energy and the K24 energy. And the link is that one bit of this energy is actually quadratic in the divergence of n. So it is well behaved. The one which is not well behaved, the one which is linear in the second gradient is this guy here. And all right, again, even if you wish to preserve the undistorted state, then you need, as the homogeneous state, then you need to set K13 equal to 0, and there is no choice. Even if you have a phenomenological theory which, on the basis of symmetry and frame indifference, has predicted it. I'm sorry. The end of my lecture. That's the battery ran out. Thank you very much.
That's not that one.
Did I kill it? Can I continue?
Yeah.
All right. All right, Erickson's inequality have been already recalled, and I need them for my extension later on. And but I wish to finish this first part of my talk by reading an illuminating passage, very humble, and spoken by, which is actually in the basic paper, which is spoken by him, and these giants, I think, is much more impressive. And I think they were completely aware of that distinction that was made in the Faetti Square paper, and they simply say, all right, we should be aware of the fact that what we have computed is a total interaction energy. We have completely ignored, in their approach, the entropic contribution to the free energy. And so we have not computed, this is what they say, we have not computed the free energy of the system on the basis of a microscopic argument. So, in a way, they say, some of the conclusions that we reached based on this argument might not hold. And I think that this was already there. I mean, I think that people should have read it more carefully, because these people were completely aware of the fact that their computation, which justified the K13 term from a microscopic point of view, had only a kind of suggestive value. And in this sense, I'm interpreting the suggestion coming from the K13 term. So I think that at this stage, we can simply say, all right, K13 term has to be, K13 constant must be 0. We have several reasons, some of which are incredibly rigorous, based on microscopic theories. But what do we learn from the way Nering and Zarp arrived at this? All right, we learn, and we use it as a conceptual tool to identify the appropriate measure of elastic distortion. Keeping in mind, once again, that this measure is related to the important bit of information that the undistorted state is uniform. So K13 term and the undistorted, the basic state, go hand in hand. All right, so we just pick up, just to get inspired, pick up an interaction potential, and this interaction potential we pick up is again an explicit interaction potential between two spins, L1 and L2 are the two spins, and it has this shape. It has one kind of Lennard-Jones isotropic potential, which depends only on the mutual distance between the two particles, the centers of mass of the two spins. And then there is this expression for the anisotropic part, which is a kind of Mayer-Zarpe interaction. And this 4 is here completely Kabbalistic. And I never asked Jeffrey why it is there. But sigma is an interaction range, and these two quantities are interaction strength. So the idea is we imagine, and we take just this avenue in the spirit of the Mayer-Zarpe reasoning, or what is my rendering of their suggestions. So we imagine that at equilibrium, the first neighbors of a given spin L lie inside the body P, lie on a sphere of radius RE, which would be the equilibrium, so to say, radius. This means that PU would be the point describing, as U varies into S2, this point P sub U will describe all points on the equilibrium sphere. Once again, I'm assuming that there is a kind of isotropic equilibrium state, and then I imagine that there is a continuous distribution of these spins, so that the spin L at the point U can be given in this form in terms of this at the lowest degree of approximation in the equilibrium radius. So in a way, I'm allowing for second derivatives of this field, which is a kind of microscopic field representing the spin distribution. So this is just a Taylor expansion, which is truncated at the second level, nothing more than that. And of course, there are lots actually of regularity assumptions which are hidden behind this expansion. LU, as I said, is the spin at the point PU. And then what I simply do, I imagine to compute this average. I computed this average in the same spirit that I computed the averages in my previous lecture. So I simply imagine that there is a uniform distribution on this equilibrium sphere of this surrounding spins, and I compute the energy. Now I'm not faking anything. This would be a kind of effective interaction energy computed around the spin L, assuming that the spin, the other spins in its vicinity are distributed in a smooth way. So this is apart from additive inessential constants, this would be the average distortion energy. And of course, I needed to plug into here the expression that I already computed of L sub U, and invoke the assumption that the vector U, which defines the sphere, the equilibrium sphere, is isotropically distributed in space, I make use of this identity. If L is a unit vector field, grad L transpose operating on L must be identically 0. And it is just a matter of a couple of computations to prove that this WE is indeed K over 2 grad L squared, apart from inessential additive constants. And the reason is pretty well, there is this minus sign here, which is actually hidden by an integration by parts, and this is the result of this very simple-minded computation. So what this rho is the volume number density, and what does it tell us? Well, it tells us, I mean, now there is a gap to be filled. I mean, I'm just going from the L field to the N field, and the N field is a kind of macroscopic phenomenological field, but I have no other tools than bare imagination. And what I'm saying is that, in a way, I believe I have pinpointed at a microscopic level by using this heuristic argument, I have pinpointed the measure of distortion. And the measure of distortion is the grad of L squared. So this tells me and teaches me a lot of things. It teaches me that I should look for quadratic expressions in the phenomenological measure, and it also tells me that there is an undistorted state which is inherently associated with this theory and with that particular interaction potential I had considered. And this isolate and this undistorted state is a state where L is uniformly distributed. So this is the first conclusion. The second is that the local elastic distortion must be minimized by grad n equal to 0. So I'm just transliterating from L to N. Of course, this is something that should be done more properly, this kind of multi-scale approach, which I think is still missing in the theory, but I wish to keep going. I cannot just be stopped by something which is missing. And as I said, the elastic free energy is quadratic function of grad n. So these are the three facts that I extract from this computation, which I call a kind of Meyer-Neringenzaub inspired computation. All right, now this works fine because this simply tells you at the start that you had no reason to invoke the K13 term. It is a kind of poor man approach. I mean, I admire Hiroshi's rigorous proof, and but I'm not able to reproduce it. Now the point is, I want to do something more. Can I go any farther inspired by this connection between the existence of an undistorted state and the K13 term? Can I repeat this argument in a completely different setting, and can this new setting tell me what to do in a situation where I don't know what to do? All right, the new setting is one of pneumatic shells. So I imagine that there's a pneumatic film deposited on a rigid surface. I'm afraid I'm not still able to tackle the deformable surfaces that Mark is concerned with. And these are just pneumatic films living on this rigid surface, which is S, and are freely gliding on it. And I assume planar degenerate anchoring, these L spins. Of course, I think of these ribbons of the molecules to be little elongated ribbons that lie flat on a surface, and they are again described by an L molecular director. Sigma is a closed orientable surface, nu is outer normal unit, and this L dot nu identical 0 simply means that all these spins are bound to live Well, it is a failure. I knew it was a failure. No, yes, I did. All right. All right, so I introduce again, in my tensorial approach, I introduce an order tensor, which is given by this. P is a projection onto the plane, and this is the ensemble average. And it turns out it is very simple algebraic computation that Q has this general biaxial form, and where n perp, n is by definition the eigenvector with positive eigenvalue. Lambda is always to be taken positive in this theory, and the n perp is just a nu cross n. Of course, in this case, defects are isolated points where Q vanishes or alpha or lambda vanishes, and again, one can easily work out these bounds. Lambda must be between 0 and 1/2. And all right, we set lambda identical equal to 1/2. It is just the same. I'm paralleling the previous approach. In the previous approach, I set S equal to 1. Now I take lambda equal to 1/2. And, well, I redo the same computation. Now I can go quickly. I simply take the same test potential. I redo the same kind of considerations. But here I need to be a little bit more careful. Instead of a sphere, now have a geodesic circle on the tangent, on the plane, on the surface. Sorry, but I can redo the same computation. But now, naturally, instead of gradients, I get second and first surface gradients of this field. Now, this L field has to be imagined as a smooth field on the surface. And I can redo the same kind of computation. Here I need to be a little bit more careful because now I need to take the average of this tensor, imagining that it is uniformly distributed on S1, and then I get as an answer 1/2 the surface projection. All right, but the answer is the same. Formula is the same. I get again that Ws, which would be the surface density energy, by this kind of argument is simply proportional to grad surface L grad L squared. So once again, I get the same lesson. And actually, this was arrived at in a completely different approach in a Monte Carlo simulation by Jonathan in one of his recent works. He realized by simply taking a completely different avenue and completely different interaction potential, he eventually realized that this should have been the right phenomenological and density, energy density. It is the interaction density per unit area. And this is, again, now we take as a continuum limit. We reason precisely in the same fashion. We take quadratic terms and this surface gradient of n, and these little k's are the surface elastic moduli. But now we come to the undistorted state. Something here is different. Can we claim that the undistorted state here is the one in which the surface gradient of L is identically 0? That's the point, because otherwise everything would be completely analogous. Well, this is not. This is clearly the turning point, because if I assume, as we have assumed, that n is tangent everywhere on the surface, then by simply differentiating this identity, I get another identity, assuming that n and nu are smooth surfaces, and this is the surface gradient of nu is a curvature tensor. Now it comes from here that if I assume that the surface gradient of n is 0 at a point, this implies that n must obey this property, and this property might not be fulfilled, because first of all, well, this is not fulfilled if, for example, all principal curvatures are positive or have the same sign. So there is something missing here. And what is missing is the fact that we need to cope with the fact that the undistorted state is not the state where Ln, or L, if you wish, in your microscopic picture, is uniform on the surface.
Is this a closed surface.
Yes, it is.
So you have to be
No, it is just a local argument. There's a fact.
There's a global consequence.
There will be global consequences. I'll come to that later on. But it is a local argument. You cannot, I mean, it doesn't make any sense to require that surface gradient over n is identically zero. Because you can't. And so, now the point is, how do we define? Now, we have exploited all our means in a way, because the microscopic argument has told us how to construct the free energy, and this is, I think, a good suggestion. Now we have constructed an energy, but the point is, how do we identify the undistorted state related to that energy? There are several ways to do it. One is to do this director representation. I can just take a system of coordinates. U and U per would be the vector field associated with the choice of coordinates. And one way to do this is by parallel transport. I simply say that one field is the least distorted one and is going to be my reference state. If given a value of n at a point, I construct the adjacent values, so the values in the adjacent point, by simply parallel transporting this vector in all possible directions. All right, there is one formal way to do it, but my chairman said I should stop in 5 minutes, so I keep it concise as I can. Well, sometimes formally this is called the spin connection or the parallel connection. This is precisely what I said in words. In a formal way can be translated in this fashion. This field which is locally parallel transported is a field which, in terms of the value of the vector which is parallel transported nearby, has a surface gradient which is represented in this fashion. All right, so this means that I can decompose my surface gradient into two parts, and we always the one which is unavoidable, the distortion which is in a way created by the surface, and I cannot avoid it. And it is a distortion related to the parallel transport of the value, and there is a correction to it. I can always write the surface gradient of n in this form, where W again is this spin connector that I introduced. An equivalent way to write the splitting is by recognizing that this bit here is nothing but the covariant derivative of n on the surface. And so the surface gradient, which is my natural measure of distortion suggested by the microscopic argument, by this analysis can be split into two components. One which is the covariant derivative of n, which is just this one, and the unavoidable, the distortion which is in the background and which is induced in the background by the geometry. So this is a covariant gradient, and now I think I still have 5 minutes, and I would like to just comment on this surface irrotationality. So on the surface, when you compute the curl, the surface curl of the surface gradient of a scalar, this is not zero, as it is in a flat space. Well, in flat space, if you compute the curl of a gradient, this is identically zero. On a curved space, or on a surface in this case, this is not the case. And once again, what surface is that combination of terms that we have already seen in the parallel connection. So this means, in other terms, that if I wish to prove that a given tangential field A can be written as a surface gradient of a scalar, well, there is only one way to prove it, and to show that the surface curl is given by this expression. So in a way, the irrotationality condition, which would simply mean that the curl in a flat space would imply that the curl of the grad is zero, on a curved surface reduces to this. And it is important to show that if I use my spin connector and I compute the surface curl of this, this is what would be needed to make it a gradient, a surface gradient of a scalar plus a correction. And this correction measures the Gaussian curvature of the surface. So it simply means that unless k is 0, I cannot make W the gradient of the scalar field. And why do I care for it? Well, I do care for it because if I write again the surface gradient of N squared, which was a kind of a prototypical measure of distortion, I can write this in this form. And this simply means that unless k is equal to 0, I cannot, by rescaling or by redefining an angle, I cannot reduce the distortion energy to 0. So in a way, if k is different from 0, there is always a distortion energy which is inherited from the geometry. And of course, in the splitting I also learned that there is, and this came actually from the fossil distortion, this proves that there is a curvature field. There's a term in the energy which acts as an electric field would act, with the only difference that this action exerted by the surface gradient. All right, this is what I already said. In this case, it is simply very simple to prove that given this representation, the K24 term vanishes identically, so you are left with this 3 constant representation, and you can explicitly write the curvature field by introducing the principal direction of curvature and the principal curvatures, and use E1 and E2 to represent, at least locally, the N field. And by doing this, you can again rewrite the general expression with K1, K2, and K3 in this fashion, and you immediately recognize that there are terms which depend on the gradient, surface gradient of theta, and terms which depend only on the coupling between the orientation of N and the curvature tensor. And these, of course, you have no control on these, and these are not ill-behaved. If you want WS to be positive definite, the only thing you need to require is that K1 and K3 are positive. K2 can be anything, just because, as you see from here, K2 is not affected by the local distortion. K2 is only affected by the curvature field. So once again, you learn that the undistorted ground state is relevant even in defining what inequalities you need to impose. So the reason why in the nematic case you have inequalities involving all elastic constants comes from the fact that in that case the undistorted state is N equally constant everywhere. So grad of N identically 0. Not being this the case, in this situation you get a different inequality. Well, and I'm just 1 minute to the limit that I was given. You can always look at these terms, which are the red terms, and you can ask yourself which would be the curvature field equilibria in this case. So for what values of theta, remember N depends on theta, and theta is the angle that N makes with E1. So the curvature lines, when sine of 2 theta is equal to 0, the curvature lines are indeed lines along which these terms are stationary, but which simply means that the stationary points, the equilibria of the curvature field, are those along for which the N vector is aligned to the principal directions of curvature. But if this ratio is in between -1 and the interval -1, 1, there are other possibilities. And actually, you can get spiraling configurations which minimize the curvature energy. So this is what I wanted to say. Again, by getting inspired by a null problem and avoiding the shortcuts that have been produced along the way, I think one could still nowadays learn from the K13 term. All right, this is the commercial. I had to shine, and thank you very much.
Are there any experiments that require K13 to have them explained? I'm asking anybody who might know.
Well, there were people who claimed there were.
Well, what one can say is that both the previous speakers who
Can you
said
speak louder?
sorry,
I know you can.
I'm sick. Listen. Some people said that, I mean, it was clear earlier on that if K13 was non-zero and you took it seriously, then indeed you had a distorted ground state. So some people said that if you look close to the surface and you find some distortions close to the surface, then what they called spontaneous distortions close to the surface, that this would be evidence for the fact that K13 was a real term. And as far as I'm aware, such experiments either were not carried out or have failed, but at least they were... Actually, Oleg, where's Oleg? Oleg, you did something like this, didn't you? Oleg, you did something, and you and Victor Pergamachik was a believer.
I'm not a speaker, so I cannot answer the questions that occur after the two
This is a...
theoretical
Oleg,
talks.
Oleg, I asked
I
an experimental question. Do you need K13?
After this session is over, I can spend 5 minutes to tell you what I think from the experimental point of view. But it would be better to separate the formal presentations on the theory and kind of reminiscence.
Oleg, it was a yes/no question. Oleg, it's a yes/no question. Do you need K13 to explain stuff?
For the things that observed so far, no. But in the experiments, you see, you always give a number and then this funny plus minus.
Yeah.
So
But the cosmological
it's
constant.
0
like-
plus minus about 1 piconewton.
Right. So I.
Yeah, that's measurable.
So this K13.
Yeah, coming from theorists, it's
Let's not go to the minus 9. So then, is there a symmetry that knocks K13 out? You didn't say there was a reason. You could have K13. It doesn't have to be 0. You calculated it was 0 in some model. Does it have to be 0? I mean, after all, you can just add all the 20 other elastic terms, and you can make it all stable if you need to. Right?
I don't need it.
I'm sorry?
I don't need it.
I couldn't hear what you said.
I don't need it.
I understand you don't, but you could put it in if there. If it turns,
Occam principle.
I mean, it's there, right?
Occam's razor.
It might not be very big. It might not be very important, but it's there.
I don't think it is there.
What does that mean? What symmetry rules it out? What symmetry? You can't tell me that it's the solution space.
No.
ruling it out.
Symmetry.
It is.
Sorry?
It's not ruled out by
Right.
symmetry.
Symmetry allows it. The point is that the ground state is no longer the one you want it to be.
Unless you add higher order derivatives.
Yeah, and they're there too.
You keep having a ladder problem, though. If you put in the second derivative due to having quadratic and first derivatives, then you put in quadratic and second derivatives, then you got to put in higher order terms.
So what do you mean? They're all there.
They're all there.
They're there. You
No,
can
they're
put them
not
in.
there, because then you get
Yeah,
to a
but-
point at which you can't be using, you're getting variations on a scale
Those are the
which couldn't
terms
be discussed by a
get an
continuum
instability.
theory. So you
Can't
really
get
do
away
have
from the
a...
instability.
Are there any other questions?
You get a linear term and a forced derivative.
Question here.
Then you got to stabilize.
So in Ian Stewart's talk yesterday, if I recall, just trying to connect some dots here, there were 6 constants, and one of them was removed by what was referred to as an Onsager principle. So that's not a symmetry principle, that's a maximum dissipation idea. Is there any view that would knock out this type of constant using a different principle, not a symmetry principle, but something else like an Onsager maximum dissipation?
There is a symmetry principle. Well, that's Tom. Tom? Right, the Onsager relations, they're the Kubo formula, right?
Yeah, they have nothing to do with elastic constants. You're not going to get.
But they also follow from symmetry.
They follow
Microscopic reversibility.
they follow from a type of symmetry having to do with. You look at the correlation function, you take the right limit, and you see.
I don't think it is a symmetry issue. I mean, it's just a stability issue. And sometimes people want to have a theory which is a continuum theory which is stable. And this is, there are instances in dynamics, for example, in which some inequalities have been enforced just on the basis of a stability principle. This would be my way. Instead of an inequality, you get an equality.
Okay, I think I will draw this discussion to a close now. Thank you very much again.